There we go.
Okay, so that is a German word, Eigenfaces, and Felipe is going to tell us all about that. So Felipe, the virtual floor is yours. Thank you.
Well, thank you. So today I'm going to be talking about Eigenfaces, something that I'm really excited about. It's actually a facial recognition algorithm. And what I hope to do in this presentation is to demystify the word algorithm and the word artificial intelligence and facial recognition, and show that in the end of the day, it's just some fancy math hidden behind some code. And so yeah, here's what we'll do in this presentation. We'll go over some linear algebra that we'll need to get the Eigenfaces algorithm working. We'll derive the Eigenfaces algorithm, and then we'll see it in action. And there's going to be some code blocks in the presentation if you're interested in that. So first things first, some core linear algebra. We need to talk about dimensions. What are dimensions? You can think about dimensions as features that we use to describe things. For example, we can describe everything in our world here using just 4 dimensions, sorry. 3 for space, so x, y, and z axis, and 1 for time. You can think about, for example, if you have a paint of some color, you can think about it as in 3 dimensions, so red, green, and blue. Each of these is a dimension. Well, vectors and matrices, same definitions from my GCSE, basically, just object of numbers. Vectors have a magnitude and a direction, as you all know, and matrices are collections of numbers and can be also thought as collections of vectors. And I'm also going to be using the concept of vector spaces and subspaces. Now, no, this is a very, very informal definition. This is not what it actually is, but it gives an idea of things that we'll be using. So if we have a vector space defined by the matrix that spans 1, 0, 0, 1, or the 2-dimensional identity matrix, then we can say that it has basis vectors b, b1, and b2 being 1, 0, and 0, 1. And with the basis vectors, we can define every single vector that lies in the space. So for example, the vector v, that's 3 and minus 2, can be composed of 3b1 minus 2b2, or more precisely, 3b1 plus minus 2b2. And a subspace is then a space that just contains less basis vectors to define its span and may also be of lower dimensions. So this is the generalized form of what I just said. If we take an n by n dimensional vector space V, where we have basis b1 to bn, then any vector in V can be formed as a linear combination of the vectors in the set of basis vectors b1 to bn. So this is just expressed as a sum from I equals 0 to n of wi, which is a scalar multiplier or coefficient, times bi. And we'll call wi the weights of this vector that define it. Finally, eigenvalues and eigenvectors. So this is where the word eigen comes from. It's really a very fancy word for a quite straightforward principle. So if you have a square matrix A, then lambda is called an eigenvalue for A if there exists a vector x such that Ax equals lambda x. So what does this actually mean? Well, if you take this square matrix A and multiply it by a vector, the vector won't change direction. It will merely be scaled by the eigenvalue lambda. And so eigen comes from German, it means 1, and it refers to the uniqueness and the importance of these eigenvalues and eigenvectors that pretty much are the identity. Identity is a bad word in this context, but kind of define the matrix. So let's look at the data set that we're going to be using during this process of this algorithm. It's the Olivetti-Faces data set. It was developed by AT&T as well as Cambridge, I think, in 1992. And it contains 400 images of 40 different people, so 10 images from each people. There are 64 by 64 pixels. And so what we can do is describe each image then as a 4096 dimensional vector. 4096 is just 64 squared, so instead of showing this data set as 400 instances of 64 by 64 pixels, we show it as 400 instances of 4096 vectors. And if you think about the definition that we laid out for dimensions in the first slide, it's the exact same principle applied. We can think of it as we can describe every single face in this data set as a vector, and each pixel is then an element of this vector. So the actual Eigenfaces algorithm, it's a simplified version of how it works. So first of all, we compute the covariance matrix for the data set. We then sort the eigenvectors of the covariance matrix by their eigenvalues in descending order, and we define a phase space where we choose the, let's say, n first eigenvectors, and the eigenvectors of our faces dataset are then called eigenfaces. And we can then use this subset to project a face onto the phase space and create a combination of eigenfaces that will represent this phase. Okay, so the first step performing eigenfaces is the covariance matrix. Now, I think most of us here have learned statistics in IB so far, so I think we all should know what covariance is. It's a measure of how one variable relates to another variable in a basic sense. So if we have a covariance matrix, then we're looking at, for this context, we're looking at how each pixel in the dataset relates to every other pixel in the dataset. So in a sense, it's kind of carrying some intrinsic information about this dataset. And then what we do is we take the eigenvectors of the covariance matrix. Now, what does this mean, taking the eigenvectors of the covariance matrix? Well, first of all, the eigenvectors sorted by eigenvalue from biggest eigenvalue, if you think of how the eigenvectors are the vectors that aren't affected in direction by the original matrix, then they show the directions of most variants in the data set as we're looking at the covariance matrix. It also shows in a kind of more intuitive way and less formally defined way how the data set contains some certain elements within it that define all images that it carries. And just one thing, notice that we have 400 faces, but we have 4,096 eigenfaces, since we're looking at the combinations of the pixels and not the faces. And then what we do is we define our subspace by just cutting up the eigenvectors to the amount of components that we want to use for our phase space, which I'll call B here. And that's pretty straightforward. And now we have computed our phase space. Now, how do we actually do facial recognition? Well, first of all, let me show you what the eigenfaces look like. So they're kind of ghostly images, and they don't make a lot of sense by themselves. But if you, for example, look at the first image, or the first eigenface, these are sorted by eigenvalues. So once again, showing like how scaled they are. Okay, so then the first one is almost black. So if you think of creating a face and you add just the first one, it's going to be a very dark face. If you look at, for example, the sixth one, there's a very dark spot on the nose. So if you add those two combined, it would be a dark face with a very intense nose. And if you look at all the other eigenfaces, they all carry some specific element to them that can be used to compose a new face. And that's exactly what we're going to be doing here. So projections are just, you can think of projections as shadows. If you have a 3D object and you shine some light at a certain angle, you get a projection that is in 2D. So you're cutting up dimensions as you do that. So if we have a new face that's not in the data set, and we project it into our principal subspace, our subspace B, the phase space, we're going to get some values here according to just how matrix multiplication works. So remember, our phase space is n by 4096, where we choose n for how many numbers we want, and times a 4096 vector, which is the phase that we're trying to project here. So at the end, we'll get an n by 1 vector, which will hold the weights used to compose this image. Now, what we do with these weights then is we go on to the original eigenfaces data set, so for the phase space. And so for the first weight, we multiply that weight by the first eigenface, then the second weight by the second, third by third, and add them together. And we also need to add them to the mean of the faces, since we need to subtract them to normalize the data set first. And then once we do that, we have recreated new faces using the pieces or the components from a data set that has completely different faces.
Right, 2 minutes, Felipe.
Okay, and then what we can do is find the minimum distance to it. This is the actual recognition part of the facial recognition algorithm. Once we have this reconstructed face, we find which face in the original data set is closest to it to make our match. And so this is the algorithm in action here. You can see I have Pedro's face and my face. And it's really quite bizarre. If you look at it, it's only using 800 eigenfaces, so that's about 20% of the available eigenfaces we have. And we can already identify who we are here, Pedro and myself. And once again, what's bizarre is that we're not in the original data set. So this is our reconstructed faces using only information from that other data set that has only 40 people there. So if you let that sink in, that's really quite amazing. And of course, I also have Dr. Hallen and Mr. Neto here. Unfortunately, their reconstructions weren't quite as neat as mine and Pedro's, but it still goes to show and the limitation that it's a very limited data set. Now, using all the eigenfaces of 4086, this is the image we get, and it's zoomed out for a reason that we can look at it in high quality, but once we zoom in, it kind of loses definition. And also kind of a table showing the progression as we use more eigenfaces to form our images, how it approximates the original image of my face. And if you look at where we're not using any eigenfaces, then that's the mean face that's computed from the data set. So some final considerations just before I run out of time is that this method, this algorithm, Eigenfaces, was developed by MIT graduates over 20 years ago. 20 years ago, it's completely prehistoric. It's completely obsolete in technology, especially in artificial intelligence. So you can think of the capabilities that we have today using neural networks and other machine learning algorithms. Also, this reconstruction was only made with 400 images of just 40 different people. So with only that, and once again, with very low resolution, those images. I did all of this in Python in a virtual programming environment that's Google's, and I'll share the link here so you can play around with it. If you need any help, just contact me. I'll be more than happy to help you. And please, one last thing, just before I ask for questions, is that it's not really the facial recognition part, but what's also pretty amazing is this. Here what we've done, so when projecting the new face into the face space, we have created an n by 1 vector, and n is much smaller than 4096, or the number of dimensions we have. So in a sense, we have greatly reduced the dimensionality of this face, and we can now use it much more easily to maybe train algorithms or just send them to people somewhere. Yeah, I'll be happy to take any questions, and that's it. Thank you for listening.
Right. Thank you, Felipe. Well, eigenfaced, egg-faced is what was left. I understood very little of that, and I'm sure other people will have questions. And nothing that you do using my face, Felipe, will produce anything fruitful, I'm afraid. No, any questions from the floor?
Well, first of all, did we understand it?
Yes.
Goodness gracious me. I mean, this is just, pardon my ignorance, Felipe. What level of maths and what level of IT would this be? Is this IGCSE, IB, or already at university level?
Well, some elements, I think there's elements of all three. So the basic definition of matrices, that's IGCSE. Then covariance and variance and more statistical terms you learn in IB, but kind of putting all this together into one thing that's more university level. And I know that 12 minutes is too little time to explain this thoroughly. So I think I'll rephrase the algorithm in actual words so it makes more sense. So what we're doing is we're getting our data set, then we compute a matrix that shows the information of this data set. And by finding the unique vectors which describe this information the most fully, we can then build new faces from that and resemble them to the original data set. So that's kind of what we're doing here. And by doing that, we can recognize faces.
You haven't come to St. Paul's, have you, by any chance, at any stage? Because we have a face recognition system in place, and it picks mine up so quickly, and it recognizes, and it looks like me actually, and then it says authenticated, and then I can walk in. But yeah, it would be interesting to see what you think of our system if we are level 1, 2, 3, 4, or 5 or whatever.
Yeah, the thing is today it's much more advanced than this. This is completely obsolete today. No one uses this anymore. It's really more of an educational tool today. So
what do companies and airports and things use?
Well, today we use convolutional neural networks, and it's kind of a black box. It's harder to explain what exactly it's doing. There's also a formal definition, but basically we're getting each pixel we have in the image, feeding it through this net of linked neurons and getting an output. And we can train this network to get accurate results. And that's much more accurate, much more reliable, and takes less computing power.
Thank you. Does anybody in the audience do high-level maths or computer science? Can you take him on, please?
Right, I think we have a question from Augusto Burkett. So, Augusto.
But then say, for example, the fingers and the hands. They're also some of the most unique patterns we have on our bodies are skin patterns and the way our skin percolates on our hands. So maybe this technology is also applicable on the more microscopic sense of our bodies and things that maybe criminals and criminal detectives would look at, could use to find things that we wouldn't be able to reconstruct in a biological sense.
Yeah, absolutely. I think it's interesting you mentioned microscopic details, and that's something that it's really advancing very quickly in medicine today. There are kind of, I don't know, I would say hundreds of medical startups that are using artificial intelligence to create all kinds of solutions to improve patient healthcare. So for example, one that I was studying just a while ago in my internship is a company that sells this algorithm that they have that before, so once the CT scan is taken from a patient's head, before it's sent through to the radiologist, an algorithm looks at this image and tries to detect an aneurysm in it. And if it does detect it, quickly send it to schedule a surgery in order to save as much time as possible as in those critical conditions. So, and that goes to show that, then again, that there are obviously lots of ethical considerations when talking about machine learning, and artificial intelligence is a very scary concept, but we also have to think of the positive sides to it. In medicine especially, it's saving lives every day, and I believe it will continue to do so.
Right, thank you. Thank you, Felipe. We'll have to leave it at that, I'm afraid. So, Fab, you can always reach out to Felipe and ask your question. I can see that there's ongoing